Hi, this video is going to teach us how to make confidence intervals for a single proportion using a normal distribution. So we're going to try to answer the question, what percent of U.S. adults are thriving? In a random sample of 1,500 U.S. adults, 780 of them are thriving, which is defined as rating their current life as a 7 or higher on a 10-point scale and rating their future life as 8 or higher on a 10-point scale. So we want to find and interpret a 99% confidence interval for the proportion of all U.S. adults who are thriving based on this definition. So we are going to start by making sure that we understand what our parameter of interest is. So what is our parameter of interest? Our parameter of interest is P, the proportion of all U.S. adults who are thriving. That is what we're trying to estimate. Now, in order to make our confidence interval, we're going to use a formula that looks like this. We're going to take our point estimate P hat. We're going to add and subtract Z star, which is chosen to give us the level of confidence we want, times the standard error, which is calculated using the formula, the square root of P hat times 1 minus P hat over N. So in order to actually do the calculation, we're going to need to find P hat, Z star, and N. Let's start with P hat. We've got 1,500 U.S. adults in our sample, 780 of them are thriving. So our sample proportion P hat is 780 out of 1,500, which gives us 0.52. The next thing we're going to want to do is find our Z star value. Now, the easiest way to do this is by going to StatKey. We know we need 99% confidence level, so let's look at how we can do this in StatKey. Okay, here's StatKey. When I come into StatKey, I'm going to go into the theoretical distribution normal, because that's where I'm going to find my Z distribution. I need to make sure that I've got a mean of 0 and a standard deviation of 1, because that's my standard normal Z distribution, and I do. Now, to find the Z star, I just click on to tail. And then right now it's got 95% in the middle. For a 99% confidence interval, I want 99% in the center of the distribution. So I'm going to click on that and change it to 0.99, 99%. And then down here on the bottom, I can see my Z star value is going to be given to me as this cutoff point, 2.575. So that's my Z star value. So now I've got Z star and I have P hat. The last piece of information I need in order to calculate my confidence interval is my sample size N, and we're given that. Now we can plug these values into our formula for the confidence interval. We've got our P hat 0.52 plus or minus Z star 2.575 times that standard error, the square root of 0.52 times 1 minus 0.52 over 1,500. Once we do these calculations, we get 0.52 plus minus a margin of error of 0.033, which gives us a 95% confidence interval of 0.487 to 0.553. So the last step here is we want to interpret this confidence interval by making a statement of confidence. And so what we can say is that we're 99% sure that the proportion of all U.S. adults who are thriving is between 0.487 and 0.553. So we're 99% sure that the percentage of all U.S. adults who are thriving is between 48.7% and 55.3%. I hope this example gives you some help in finding confidence intervals for a single proportion. This video is going to work through an example doing a hypothesis test for a single proportion using the normal distribution. This is also sometimes called a z-test. So we are going to test Mendel's theory. One of Gregor Mendel's famous genetic experiments dealt with raising green pea plants. And according to Mendel's genetic theory, under a certain set of conditions, the proportion of pea plants that would produce smooth green peas should be P equals 3/16, or that's equal to 0.1875. A sample of 556 plants from the experiment had 108 smooth green peas, and these were grown under these conditions. We want to know, does this provide evidence of a problem with Mendel's theory, and that the proportion is actually different from 3/16? So we're going to work through all the steps of a hypothesis test. First of all, we're going to test at a 5% significance level. Now we want to choose our P, which is the proportion of pea plants with smooth green peas when grown under this set of conditions. That's going to be our parameter of interest here. We're going to test hypotheses about this proportion P. First step we're going to do is to state our hypotheses. So we need to state a null and alternative hypothesis. Here we're trying to decide if the sample provides evidence that P is different from 3/16. So that's going to end up being our alternative hypothesis. And our null hypothesis is going to be that P is equal to 0.1875. And our alternative is that P is not equal to 0.1875. I did a not equal to sign here instead of a greater than or a less than, because we're only looking to see if it's different, not necessarily whether it's higher or lower. So this is going to be a two-tailed test, and I know it's two-tailed because I have that not equal to sign in the alternative hypothesis. The next step I'm going to need to do is I'm going to need to calculate a test statistic that helps me measure how unusual this particular sample would be if the null hypothesis is true. So I'm going to use this formula for the test statistic, z equals p hat minus p0 divided by the square root of p0 times 1 minus p0 over n. To do this, I'm going to need to find those values to plug in. My p hat is my sample proportion, and the sample, 108 out of 556 plants had smooth green peas, so that is a sample proportion of 0.1942. I also need p0. I get that from my null hypothesis. My hypothesized value is 0.1875, p0. And then the last value I'm going to need to plug into this formula is n. N here was 556 plants. And so I can plug these into my test statistic formula. And when I do, I get a value of the test statistic of 0.405. Now, don't stop here. Don't forget that once we calculate the test statistic, the whole reason we do this is so that we can then go and find the p-value. But this is not the p-value. This is just the test statistic. We only calculate this so that we can use it to find the p-value. So what's our next step? Well, it's going to be to use the z distribution, the standard normal, to find the p-value. So we're going to be looking for the values in the standard normal distribution that are farther from 0 than 0.405, and we're going to figure out what the area is out there. So let's look at how we do that with StatKey. Okay, so here we are in StatKey. We need to go into this theoretical normal distribution. Now this is, if our null hypothesis is true, this test statistic has this distribution, this standard normal distribution with a mean of 0 and a standard deviation of 1. Now we're doing a two-tailed test, so I'm going to click on two-tail. And right now it's got a cutoff value here at 1.96, but I need to make the cutoff value the value that I found for my test statistic. Now if my test statistic were negative, I'd come down here. But my test statistic is positive, so I'm going to go up here and change the upper limit. And I'm going to change it to the value of my test statistic, 0.405. That was my test statistic. So the p-value is going to measure what's the chance I would have seen a test statistic of 0.405 or even farther from 0. So this is a two-tailed test, so I'm going to find the area in this one tail, which is 0.343, and I'm going to end up doubling it to represent the area in both tails, and that's going to be my p-value. So this 0.343 is what I need to bring back out of StatKey. Okay, so my p-value is going to be 2 times 0.343, which gives me a p-value of 0.686. That's my p-value. Now I need to use that p-value. I'm going to compare it to my significance level. Using a 5% level of significance, my p-value is larger than that 5% level of significance, which means that I fail to reject the null hypothesis. And when I fail to reject the null hypothesis, what this means in terms of the context of the problem, I need to make a conclusion, which is that the sample does not provide strong evidence that the proportion of smooth green peas is different from what Mendel's theory predicted. Hope this example helps you as you work with hypothesis tests for single proportion.